Hello everybody, this is Gary Marr of Glendale Community College. This screen capture is from my CIS 150 AB online class, and in this screen capture I want to talk about topics covered in Section 2. Section 2 starts off discussing identifiers. Now an identifier identifies something, and what it's used for in logic and also programming is it's a way for us to associate a name with something that's stored in our computer's memory. So in this particular slide, I have a variable called answer. I have a constant called pi, which are English words which correspond to something that resides in the computer's memory. Now, typically with some other computer languages like machine language or assembly language, we would typically have to identify that location as an address, typically in a hexadecimal format. This gets very complicated very quickly, so the ability to name a part of memory with an English-like name is a real advantage and helps us be more productive as programmers. Now, these variables and constants essentially identify parts of the entire puzzle called logic. A lot of times I refer to these particular items as being like screws and nails when it comes to building something. Usually with, if we're going to build a doghouse or a house, we're going to have wood, plywood, roofing, shingles, maybe sheetrock, all of which serve a purpose in constructing that home, but are held together by screws, bolts, glue, nails. That more or less what identifiers remind me of. They kind of run through all of the logic and kind of hold everything together in terms of coming up with a solution. So let's start with that. Let me talk about variables and constants individually first. A variable, by definition, is something that's variable or changes. This particular name references memory values that could change in the course of the logic or program. So, for example, this particular slide shows a variable called answer that starts off as 0, goes to 0 plus 100, and finishes at a value of 77. So it can change. Most of the time, this will be the most common identifier used in your logic. But there's also that scenario where you're going to want to have an identifier that doesn't change, that remains constant or a constant. In this case, I use the value of pi, 3.14. It could be sales tax. It could be any number which is going to essentially stay true while the program is running or the logic is being running. You're going to find out a little later in this discussion about magic bullets, which are a form of constant that do change from program to program execution or logic to logic execution. But for the most part, when you have a constant, it's not going to change. Constant by convention typically have uppercase letters in their name. What we want to try to do during this course is introduce you to as many programming standards or conventions as we can. If you become a professional programmer, you're going to want to follow those industry standards that other programmers use. Typically, with variables, we use lowercase, camel casing, or Pascal casing, and that's a combination of upper and lowercase letters. But constants will always typically be identified as uppercase. That way it's a signal for the person looking at the logic to say, hey, wait a minute, this is different. It is a constant. This value will not change as I read through and better try to understand this logic. All identifiers, and with constants it's a little bit different than with variables, have these 4 acronyms. The actual definition of the variable, where you give it a name and typically a data type, a number, text, single precision, decimal, floating point. An initialization piece, which sets its initial value. A lot of languages now by default will set all numbers to 0 and all text to empty. That's not always been the case, and it's always a good programming convention to set the initial value of your variables just to avoid any confusion later on. The next action is referencing the variable or using it within an expression, calculation, assignment, etc. And then also, because variables can change, I can reassign the value. So the assignment is also something that takes place when working with variables. Constants, not so much. As I said before, it's a good idea to make your constants uppercase. In this case, tax is an uppercase assignment of a constant. The tax rate would be 0.05. I should also talk a little bit here about the other pieces of this puzzle here. Total cost and sales would be variables. they're not uppercase. And one thing that's important to point out here is total cost is actually called Pascal casing. That means every word that's inside the variable name is capitalized to make it easier to read. There's also something called camel casing, which would be the variable starts with lowercase letter, but then every word that's added to that variable has the uppercase letter. And the reason we use these upper and lowercase letters in identifiers is to make them stand out and easier to follow. A lot of times you want to make your identifiers as easy to understand and describe actually what they hold, but you don't want to make them too wordy or too long, because all that's going to do is create typo errors, and it's going to lengthen the amount of time it does to create the actual logic program. So you want to keep them short. In camel casing, Pascal casing, there's also something called shish kebab casing, and snake casing, and these are particular variables or identifiers identified with either a dash or an underscore. It makes it easier to read. Whoops. This slide is a good one to just reinforce what I said earlier. Here we have a variable called total, and that's what our program logic is going to use it or know it as. But yet, in fact, when it's running the computer, that particular variable total has been mapped to a particular address, in this case 200. And that address 200, it's going to hold the value of $66.32. It's much easier for us to refer to this location in memory by its variable name than it would be by its address. And some of the older programs, some of the first programming languages, the older ones, did exclusively use memory locations. These programs are very fast, they're very efficient, but they're also very complicated to read. Identifiers versus keywords. Identifiers typically are going to be a word, no spaces. They're going to be short enough to define accurately what they actually hold. But there are some rules and regulations in terms of what they can and cannot be. One of these rules involves conflicts with keywords. All programming languages, and again, pseudocode doesn't have this issue because pseudocode doesn't have any standards, but if I was programming in Java or Python, there's certain terms or words reserved by that computer programming language to perform certain activities or actions, verbs if you will, print, if, while. Some of them are very common to all languages, some are very unique to that particular language. But you cannot name an identifier the same as a keyword, because obviously that would confuse the program in terms of processing the logic. Print's probably the best example, and that's the one I listed here. Identifiers also have data types, and some programming languages are strongly typed and some are weakly typed. What this means is this. In Python, for example, if I create a variable called car, I can at any time store a number or text in that memory location. Other languages which are strongly data typed, because Python's weakly data type, strongly data type languages have rules in terms of what that identifier can store in it based on how it was declared. If you had declared an identifier to hold an integer, which doesn't have a decimal, and yet you try to put a decimal in that variable location, it's going to chop off those decimal values to the right of the decimal. Or if you try to store a text value inside a number data type, that is not going to work. You'll see this in some of the pseudocode examples we'll do later in the course. And a lot of this discussion in Chapter 2 is very early in the course, so therefore we'll build on it as we go. And if it's a little fuzzy now, hopefully we'll have some examples both in pseudocode or Python or flowcharts will help reinforce the understanding of what these concepts and terms mean. And if you do have questions, you can always send me an email. Expression is basically the next step of, I guess, building that doghouse. It's one thing to have an identifier, but we also need to be able to provide assignments and calculations or particular activities that are going to perform some sort of logical function for our final solution that we're trying to solve, or that business problem we're trying to solve. Expressions, typically, the best way to describe them would be a calculation, and then you'll also be very comfortable with assignments, because all an assignment is, as I mentioned in the earlier slide, is simply storing a new value in a memory location. And we'll see a lot more of this as we build our pseudocode. Operators. Now, this one is an arithmetic operator. It's your plus and minus and multiplication and division. This is all fairly common. If you've used a calculator, you've used these before. the only thing that's important to remember with operators is that there are rules involved in operators that will perhaps give you an answer different than you predicted because of something called operator precedence. And basically what it means is the order of the operators are evaluated based on logic built into the computer, and you have to abide by that logic if you expect to get the correct answer. So down here at the bottom of this slide I have three variables, and their variables they're uppercase, but they only get single letters. They're just for example purposes. One has a value of 2, that's the letter A, capital B is a 5, and capital C is a 6. If I want to create an expression, which is a calculation that says add A to B times C, what would the answer of that be? Well, if we approach this like we did in the first or second grade, we'd say an A, which is a 2, plus 5, which is the B value, times 6, and that's how we do the calculation straight across like that. So 2 times 2 plus 5 is 7, times 6 would be 42, I guess. Now, that's not how the computer's going to look at it. The computer, because the order of precedence, is going to do the multiplication first. It's on the same order of precedence as the multiplication. So we have to multiply B times C, okay? And then we have to add the value of A to it at the end. So it's 5 times 6 plus 2, which is 32. Now, if there's many ways to put expressions together, and they all could be right. Now, this one has no parentheses in it, but parentheses is kind of our wild card in this situation. If we want to make this look like a more traditional calculation that we first learned with, where we went straight across from left to right, what we could do is we could put the A plus B inside parentheses. And since parentheses is the highest order of operation, it would do that calculation first. Then it would do the multiplication to C, and we'd get a different answer and one that we're more familiar with. What typically happens here is that we all are creatures of habit. You will forget this. And sooner or later, you will have a program that will work fine, but it will give you the incorrect answer. It will not be 2 plus 2 is 4, it will be 2 plus 2 is 6. And you're saying, oh my God, what happened? You will use something called a debugger, which is a tool that's built into most software IDEs, which stand for Integrated Development Environments. These programs help you put your code together. These IDEs will let you walk through the code line by line, watching it execute, and you would be able to see how the variables and the constants changed as the program's been executed. You would get to the statement that you had maybe forgot about these rules on, and you would expect that perhaps A plus B plus C would be something much different than 32, but it would not error because essentially computers will do the wrong thing if that's what you tell it to do. But since you wanted it to work where the A plus B was actually calculated first, you would need to insert parentheses. The fact they're not there is what's called a logic error. There's nothing wrong with the syntax of the program. The computer can execute it, but it's not logically correct. Because you formed the expression incorrectly, you created what's called a logic error. A lot of times you can spot these just by looking at the code, but there are tools called debuggers, which we'll look at in this course when we get to the Python piece. Debuggers aren't going to help us at all with pseudocode. In fact, operator precedence is not a factor in pseudocode either because we can't execute pseudocode. But if we convert our pseudocode to Python, it will show us where the problem is. We will be converting a lot of this pseudocode to Python during the 16 weeks of this class. One of the reasons is that because pseudocode is a non-standard language, anything goes, including bad things or incorrect things. Whereas if we put it in Python, Python is very much like pseudocode. We have to make a few changes to accommodate the language, but we'll then be able to run that logic through Python and see if it actually works the way we expected it. And if it didn't work the way we expected it, we'll be able to use tools like debuggers to find out why. This is a lead into this slide. There's basically three kinds of errors that you can run into with logic. There's a syntax error, which typically is a typo, a variable that's got a space in it. You can't have any kind of identifier with a space in it. It has to be letters straight across. You could have underscores, you could have dashes, but no spaces. If you did that, you get a syntax error. There's logic errors. The logic errors are one I just talked about. Another common logic error is on logical operators, where it's greater than or less than or greater than or equal to or less than equal to. It's very easy to forget that maybe it should have been greater than or equal to. You only have greater than, The program works fine, but it's not calculating correctly. And again, the debugger would be used to help you find what you logically put in incorrectly. Lastly, there's runtime errors. Runtime errors are things that do not compute. In other words, there's no syntax error. They're formulated correctly, the statement or expression, but the computer can't run it, and you can't fix it. Dividing by zero is one of these. You cannot, with a computer or a calculator, divide by zero. It'll tell you it's indeterminate. That's the classic example of a runtime error, divide by zero. You will learn more about runtime errors as we get into other topics in class. The other kinds of runtime errors that are fairly common. A minute ago, I talked about debugging of your code or of your logic. We can't do this in pseudocode. We can't do this in flowcharts, but we can do this in something like Python and also Java, JavaScript, C#, C++. What this is a special facility that's built into the programs that you build your code with, that before you execute the program or complete the execution, the building of the program, you can run it through what's called a debugger. This is especially valuable if you think that you're getting an incorrect answer, or you know you have an incorrect error, but you're not sure where it's happening. What you can do is go into that debugger, set what's called a breakpoint, and it's usually just a little click on the outside of the line of expression, and the program stops there. And when it stops there, you can now hold the cursor over the top of whatever variable or constant you're interested in looking at, or you can also display the information typically on the side. It'll tell you at that point in time, this is what these identifiers are holding. If that's not what you think there should be holding, then you've got an error, and you can now take and use the debugger to step through the code line by line to find out exactly what went wrong. Typically, you're going to step into the code, and once we get into the creation of modules or functions, there is also the ability to kind of jump around in a bigger hop called a step over. But all this will be explained or built upon later in the class. Right now, it's mostly just to let you know there are tools available to help you understand some of the problems that you can run into with identifiers. All right, so this is the end of the second lecture, and you're going to find that even though the lecture will cover PowerPoints, the main topics of class, there'll be a healthy dose of other videos that I'll be creating that will go through specific examples and hopefully give you a little better perspective in terms of what's happening, what it means, and if it's a problem, how to fix it, or if it's something new, how to build it yourself. If you have any questions, please let me know.